So let f of x be the function shown in the picture below. Ah, what a lovely picture. And we're given that g of x is f of x times f of x. And we're asked to find g prime of 2. We were given 5 options. 1, 2, 3, 4, or 5. What's the answer? 1 is correct. So, no big surprises. Hopefully by this time we're pretty good at this kind of thing. We take the derivative, use the product rule, use the chain rule, plug in 2. We know information about the function at 2, namely its value and its derivative. Then we say, well, we see an f of 2 being plugged into f, so we need to know what happens at 5. So we know the value of the function and its derivative, plug everything in and simplify, and you get 1. All right, good. So, thought for the day. This comes from a 1960s British television show. I am not a number. I am a free man. Said by number 6. So, this was, in case you're wondering, this is from The Prisoner. And number 6 was the main character. We never learned the actual character's name. He's just referred to as number 6 the entire time. They're trying to break him. It's a psychological fun. It's a really weird show. Like, if you enjoyed things like Lost, you would like this show. If you didn't enjoy Lost, you still might like this show. But anyways, why this? Well, because after you take a test, there's a tendency to think of yourself by your score. Like, oh, I am a 55 out of 70 calculus student. But no, you are not your exam score. You are not a number. We don't look at you and say, you're a 70 out of 70. You deserve love and praise. 60 out of 70, you're great. 50 out of 70, you're doing wonderful. 40, keep at it. 30, we don't do that. We don't say that. So regardless of your number, we still like you. We still want you to succeed. And I do want to emphasize, while it is true that the first test is somewhat predictive of what will happen in the course, it does not have to be. Nobody in Calc 1 has failed the class. Nobody in Calc 1 has gotten an A. Everybody can pass. Everybody can get a B. A might be stretching it for some, but everybody can get at least a B. Now, it's possible. So I don't want you to abandon hope. Because you're here, I'm preaching to the choir when I say that. You're showing up. You're doing the work. Keep doing that. Keep doing the work. Another thing I want to say is oftentimes when people think about their scores, I didn't say this earlier, but I want to say it now, they tend to sort of think of it as like it's a 0-1. Either I know or I don't know. But I don't believe that. I think there's a whole range of values in between. And I think a lot of people are much closer to getting good scores than they know. It's just small mistakes, small errors in understanding. And with that work, you can overcome that. I still believe in your potential. Regardless of what you got, I still believe that you can learn. So, all right, now on to today. So we're going to talk about explicit functions versus implicit functions. Now, explicit functions are the functions that we're used to. So when we talk about explicit functions, they're the ones that we've been writing down for a long time. So for example, if we want to write down explicit functions, we can do things such as f of x equals x squared plus 3x plus e to the x. That's an explicit function. Because what it is there's this machinery, this rule here, and you plug in an x, and I can run through the machine, and I can see what's going on. So if we think of our function as this box here, I can open the box and look inside. And I can see, oh, I see you take x and you square it, you add 3 times what you put in x, and then you add e to that power of x. So I understand everything that's going on. So this is an explicit function. And we have rules, and they're wonderful rules. We know how to take derivatives of many things for an explicit function, and we'll pick up a few more in the next few weeks. But then we get to implicit functions. And implicit functions are basically things that aren't explicit. So what do they look like? Well, you have stuff involving x and y equals other stuff involving x and y. So you can have some things such as, I said examples, but I only wrote down one. So I should write down a second one, 2x plus 1. There we go. So examples. You could have things such as x squared plus y squared equals 25. Now, you might say, wait, hold on. I understand that. X squared plus y squared equals 25. What is that? A circle. Can you tell me anything else about this circle? Radius of 25. All right, let's just quickly graph that, and then I'm going to ask a question. Does this give y as a function of x, and why not? All right, I guess that was 2 questions. Does this give y as a function of x? No. Yeah, you're right. It doesn't give y as... Good. Why not? Oh, right out of the bat. Boom. There's something called the vertical line test. So you might remember when we talked about functions, there's a function has to have the following property. No matter what you put in, you have to get the same thing out. So there's a consistency. Well, the problem is if you pick a value for x, well, you might get 2 different values. And so you're not getting one value out. So that's why it's not an explicit function. Nevertheless, it's a curve that we probably would like to be able to understand. But you can get things much more exotic. You can get things such as x squared y plus e to the x times y plus cosine of x is equal to 2. Now, x squared plus y squared equals 25, you can always cheat a little bit and say, well, I can figure out the top half. The top half would be when y is positive square root of 25 minus x squared. And I can sort of do the bottom half in a similar way. Namely, the bottom half would be if y is negative the square root of 25 minus x squared. But is there any hope to do that here? No. It's hopeless. It's hopeless. Now you might say, well, wait, so does that mean that y and x that y is not a function of x? Well, no. There is still a relationship. So that is to say, if you give me an x, it determines the possible y, or possibly several values of y that can work. So there's some rule. The problem is we don't know what the rule is. In terms of our box here, we cannot open the box. There's not a procedure that we can follow, a recipe, if you will, that we can follow to make the function. So the question, is it even possible to talk about calculus for these implicit type functions, these implicit relationships? Well, I mean, in some sense, what's the goal of calculus? Our goal of calculus is to say, how are things changing? That's our goal. And so it's a reasonable question to ask. Well, if I change x, can I talk about what's happening to y? And it turns out the answer is yes. Okay. So that's the punchline there. Implicit functions are still functions. We just don't know what they are exactly. But we can still take derivatives. Now, the way we do it is we're going to rely on the following idea. If 2 functions are equal, then their derivatives are equal. Is that true? Is that reasonable? Yeah, it's a true statement. If I start with two things which are the same, their derivatives are the same. We can even do a really simple example of this. Let's start with two things which we know are equal. So let's suppose I look at the following. F of x equal 1 and g of x equal cosine squared x plus sine squared x. Now, are these two functions the same? Does cosine squared x plus sine squared x equal 1? True story, they do. So let's talk about their derivatives. Which one do you want to do first? Oh, you want to do the g first. Wow. Bold move. Okay. So let's talk about g prime. What's the derivative of cosine squared?
Negative 2 sine squared x.
Well, so cosine squared x is always saying cosine of x squared. Does that help? 2 comes down. Cosine of x to the 1. Anything else? Negative sine x. Why the negative sine x? Chain rule. Okay, how about this sine squared x, which we can think of as sine of x squared. What's that derivative going to look like? 2 times sine of x times derivative of sine, which is cosine. So, the first term we have 2 times cosine times negative sine. The second term we have 2 times sine times cosine. Does that simplify? 0. They cancel each other out. Now, what about f of x? We didn't do that one. What is f prime of x? 0. See, it worked in this case, but it's always going to work. Because if two things are equal, then their derivatives have to be equal. And this comes back to the idea of saying, when we think of a derivative, it's basically acting like a function. It's where we put in some f, out comes some f prime. And the rule for functions is there's consistency. All right. Now you might say, okay, but how does that help us? Well, this is our big idea. Everything boils down to this. It says, you know what? Even if we don't know exactly what the function is, we're going to think we do. So when I think of our relationship, x squared plus y squared equals 25, that tells me that y depends on x in some way, but I don't know exactly how. So I'm going to think of y as being a function of x. So in our mind, and since we're doing it today, we would write the following in our mind. We're thinking of it as x squared plus y of x squared equals 25. So when we think of it in this way, what that tells us is it tells us, hey, I have two functions of x which are equal to each other. If I have two functions of x which are equal to each other, what's going to be true? Their derivatives have to be equal. So we're going to take the derivative of both sides. All right. So we pick a side. We'll start with the 25, perhaps. Derivative of 25?
0.
All right. Now to here. So when we talk about taking the derivative, I want to be very clear. We're taking the derivative, and you might say, yes, you already said that, with respect to x. So that last part I just want to emphasize. We're taking the derivative with respect to x. So let's go through our terms here. The derivative of x squared, what will that be? 2x. Cool. The derivative of y squared, which we're thinking of in our minds as y of x squared, what will that be? 2 y of x to the 1 times y prime of x. All right, and the great aha has happened because now we say, okay, if we go back, we said y of x is y. This says 2x plus 2y times y prime equals 0. And what is it we're after? We're after the derivative. Do we have the derivative here? It's right there. That y prime, that's what we're after. So, given that that's what we're after, what do we do next? Yeah, we isolate it. We solve for the y prime. Okay, so now we're going to solve for y prime. So we can say, for instance, 2y y prime equals minus 2x. So y prime is minus 2x over 2y, which is minus x over y. Okay, so we've already mentioned what this is. This is our circle. So we can just quickly sketch our circle. This circle has radius 5. So there's a point here at x equals 3, y equals 4. I claim 3 squared plus 4 squared equals 25. Classic Pythagorean triple. What's the tangent line at that point? Well, okay, someone said negative x over y, so let's be careful here. Is negative x over y a tangent line? No. It's not a line, among other things. But what do you need to do with this negative x over y? Plug in. What are we plugging in? Yeah, we plug in the data. And here, it's not you plug in x, you plug in both x and y. So you say, okay, so here, we say, look, at the point x equals 3, y equals 4, we will get negative x over y. Now, is that our line? And why not? It's the slope of the line. Okay, so how do you go from slope of a line to line? Point slope. Do we have the point? Do we need to find the point now? Spoiler alert, it's right there. 3, 4 is our point. There's our slope. So we're out of space, but that's okay. We can pretend like we have space. Y minus the y value is equal to our slope minus 3/4, x minus our x value. So this is our tangent line. Now, could we have found this in a different way? Yes. For this case, yes. Because I talked about how we could represent the top half, we could figure out explicitly y equals the square root of 25 minus x squared. Taken that derivative, plugged into there, we would have gotten the exact same answer. However, it would actually look a lot worse because square roots are involved. So somehow, it's nicer this way. All right, questions? Okay, so key ideas. Take the derivative of both sides with respect to one of the variables. Now, usually we're going to think of our variables are y and x. They don't have to be. So the question is, what derivative are you after? What's changing with respect to what? And then you say, okay, you always have in the back of your mind. So every time you do an implicit derivative, let's say y is a function of x, you always are, this is your thought. This is always your thoughts. Like, y is a function of x. And just remember to apply the chain rule correctly. And as you apply the chain rule, you're going to see every time there's a y involved, there'll be a y prime term. Now, once you've taken your derivative, all your y prime terms are going to be on the outside of things. There's no y prime terms on the inside of things. What that means is you can rearrange and you can solve for y prime. There's no fancy arithmetic. It's just like all the things on y prime go on one side, the things without y prime on the other side, and pull out a y prime and divide. So there's nothing fancy. Just make sure you work through it. Now, there is one comment down here. If you're evaluating, evaluate as soon as possible, but not sooner. So in particular, if you have to say find your derivative at a point, it's better to plug in before you find y prime than to first find y prime and then plug in. So let's try this out. Okay. So we'll make up a function, or we'll make up an implicit relationship. So give me some pieces you want to have here. What are some terms? Sorry, what? Okay. All right. E to the yx. All right, that's x times y. All right, there's a piece. What else do you want in this function? Plus?
Yx squared.
Yx squared. Okay. That works for me. Anything else? Let's throw in a cosine 2x. And we'll set all of that equal to 2. Now, there's always the question, is this actually a curve or not? And don't worry about that. If we've done our job right, it will be a curve. If we haven't done our job right, there won't be a curve. It was like 5-6 years ago, there was a question we asked on the Calc 1 exam 2. And it was like, find the derivative of this function. And I had to point out to the person who wrote the question after the test, you know that this function isn't defined anywhere. Like, yeah, that's okay. They can still take the derivative. We're just testing the rules. So, all right, here we go. So we have our implicit relationship. Do we see that it's implicit? Other than the fact I said implicit in the sentence, what are some things that sort of indicate implicitness? Yeah, like multiple y's and multiple x's. That's an indication of implicitness. And like it's basically, if it's hard to solve for y, it's implicit. Okay, so now that we know it's implicit, we say, all right, we're after the derivative. So we want to find dy over dx. Okay, so we're going to take the derivative. Reading our notation, where are we taking the derivative with respect to?
X.
Taking the derivative with respect to x, because we see a dx. If I had said find dx dy, because you can ask this question, what does this say to take the derivative with respect to? Well, I'm asking, oh, wait, no, you meant the variable y. Oh, gotcha. Yes, you're correct. Yes, this is with respect to y. All right. Okay, so dy dx. All right. So, with this in mind, we're going to take the derivative with respect to x. Let's go term by term. What is the derivative of e to the xy with respect to x? Okay.
E to the xy.
Well, so what's our rule involved? We have a couple rules. First off, if you think of it this way, what's our first layer of rule that we have? What's your first layer? It's a chain rule. xy is inside of the exponential function. So the first layer says take the derivative of the exponential function. The derivative of the exponential function is the exponential function. And then you plug the inside back in. Okay, so this is the beginning of the chain rule. Times by what? Somebody said product rule. Times by the derivative of the inside. What is the derivative of xy? Product rule. So derivative of x, 1 times y plus x times what? times dy dx. Now you can write dy dx or you can write y prime. I tend to write y prime because it's shorter, but if you want to write dy dx, that's fine. Okay, so that's the first piece. Okay, our next piece, y of x squared. What are we going to need to do to take that derivative? Product rule. Okay, so what does the derivative look like? Y prime x squared, the derivative of the first times the second, plus 2yx. You can, by the way, also put this as 2xy. So here, the first term is the derivative of the first, y prime times the second, plus the first y times the derivative of the second, derivative of x squared is 2x. Okay, now we get to the third term, this cosine 2x. How do we take that derivative? Derivative of cosine? Negative sine. Negative sine 2x. We're doing the chain rule. Anything else? Times a 2. So that when I say we're doing the chain rule, it's like we're leaving the inside as is, and you have to multiply by the derivative of the inside. Now, have we finished the job of taking the derivative? No. What's missing? You have to take the derivative of both sides, right? We've taken the derivative of one side. So make sure you take the derivative of both sides. So it's not equal to 2. It's equal to what? Some people already said it.
0.
Good. Good. Don't forget that. All right. Now, that we basically have done steps 1 and 2. You know, we take the derivative of both sides. We've made sure to apply the chain rule correctly. Applying the chain rule correctly means whenever you see a y involved, we know it really means it's a function of x, so we have to account for that. So we're not after the derivative at a particular point, so that means the last thing for us to do is to now get the y primes together. How many y primes do we have? We have 2 of them. So the things with y primes we'll leave on the left-hand side. So we have an x e to the xy times y prime, and we have an x squared times y prime. So we have that term and that term. Things without a y prime, let's move across. So this 2 sine 2x will move across, become a plus 2 sine of 2x. This 2yx moves across, minus 2yx. And then this term, e to the xy times y, that will also move across, and that's going to be minus y e to the xy. So we kept the terms with y prime on one side, the terms without on the other. All right. Cool, 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 cool. Well, now what happens? Yeah, you factor out the y prime. X e to the xy plus x squared times y prime equals, and then everything else on the right-hand side. And finally, to get y prime by itself, we have that y prime, also known as dy over dx. They mean the same thing. 2 sine of 2x minus 2yx minus y e to the xy, divide by x e to the xy plus x squared. And now you can plug in any value you want for x and y, and if you do that and you carefully work things out, you will find your derivative at that point. All right, so that's the process. Any questions? Yes?
When you distribute the e to the xy, should the e to the xy, how does it become x squared to the y y prime.
Well, that came from here. So what happened is the distribution, half of it stayed on the left, half of it moved across. All right. Well, you ready for another problem? Okay, some notation. I don't know if we've used this notation yet, but in case we haven't, if you ever see a big bar, that means it's an evaluation. So we want to evaluate the derivative at a point. So if you see dy dx, big bar a comma b, that says what's the derivative at the point a comma b. So you have a curve. 2x squared plus y cubed equals 3xy plus 3, and we have to find the following. We need to find dy dx at the point 2, 1. What is the tangent to the curve at the point 2, 1? What is the normal to the curve at the point 2, 1? So, side note, what is the normal line? Do you know what that means?
Wouldn't it just be the 2x squared?
It's what? Perpendicular. So when you see normal, normal stands for perpendicular. So how do you know a line is perpendicular to a curve? You're perpendicular to a curve if you're perpendicular to the tangent. So if, in general, when you see the word normal, there's this notion of perpendicularness going on. You should think of it, does it mean perpendicular? And usually it does. All right, so we're after some things. In the interest of time, we will go through this together at a bit of a pace. So, we're taking the derivative of y with respect to x. In our mind, and by the way, you don't always have to draw this, but this is just to emphasize, we are going to make sure that we think of y as a function of x. So let's start by taking our derivative. We're taking the derivative of both sides with respect to x. What's the derivative of the left-hand side? 4x, good, plus 3y squared. Is that it? I'm sort of hesitating. Y prime. Where did this y prime come from? Chain rule. We're taking it with respect to x. So y is a function of x. So this is y is a function of x cubed. So 3 comes down, y is a function of x squared times the derivative of y. And the way you write derivative of y is the derivative of y. Equals, on the other side, 3 times xy. What's the derivative here? Three y plus 3xy prime. So it's the derivative of the first. Derivative of x is 1, because we're taking the derivative with respect to x. And so y just stays as is for right now. Plus, now the x stays alone, take the derivative of y. And the derivative of y is the derivative of y. Okay, so we've taken the derivative. Now, we want the derivative at a particular point. So, do you want to plug the point in now and then solve for y prime? Or do you want to solve for y prime and then plug in the point? Someone wants to do it the hard way. Now, will you get the same answer? Yes. I encourage you to follow the rule of thumb, substitute as soon as you can, but not sooner. So, I'm going to plug in x equals 2, y equals 1. That's this information here. So 4 times 2 is 8. 3 times 1 squared is 3. Y prime is the slope we're after. Equals 3 times 1, which is 3. 3 times x, we come 3 times 2, which is 6. Y prime. Well, move stuff around. Subtract the 3. Subtract 3y prime. 5 equals 3y prime. What's y prime? Five over 3. 5/3. Now, this represents how y is changing with respect to x at the point on the curve. What can we interpret this as? So this is rate of change. This is also our slope of tangent. Because we look and say, hey, you need to find the tangent. Well, can we do that? Yes. Because what do we have? We have a point. What else do we have? We have a slope. So y minus the y value. So this is number 1. Y minus your y value is equal to your slope, x minus your x value. So this is your tangent. You don't have to simplify. You can just write it in that form, no problem. Now how about the normal? How much work do you have to do to write down the normal?
Don't you just have to make the 5/3 negative and you get 3/5? Or negative 3/5?
Okay, so you said make the slope negative 3/5. Where is that coming from?
It's the opposite of the slope.
Right. Negative reciprocal,
Yeah, that works.
which is a fun way to say they have to multiply together to give you -1. So you change the sign, flip it over. And there's your normal. And once you write it in this format, then to go from tangent to normal is very easy. If you simplify and then say, now I got to write the normal, then there's a lot of work going on. Okay, so now that was a good warm-up. Any question there? Good, so we have some time. So, the curve 2x squared plus y cubed is equal to 3xy plus 3. What's the second derivative of y with respect to x at the point 2, 1? Is that possible to find? Yes. How do you find the second derivative? Take the derivative of the first derivative. Now, you could solve for dy dx and then put yourself through a torturous quotient rule. I do not recommend that. Here's an idea. Here's one derivative. That got us to the 4x plus 3y squared y prime equals 3y plus 3x y prime. So what can we do? Take derivatives again. Derivative of 4x, 4. Derivative of 3y squared, 6y, y prime, times y prime. Okay, don't forget the chain rule. Plus 3y squared times what? Y double prime. Equals derivative of 3y, 3y prime. Derivative of, here we're going to use the product rule. We'll have derivative of 3x is 3, y prime, plus 3x times y double prime. Now, what do we know? We know where we want. We know x equals 2. We know y equals 1. But what else do we know? We know y prime. We've solved for it. We know y prime is 5/3. So what do? You plug all that in and solve for y double prime. And then we're happy. So that's about time. We have a minute left. So this is the kind of question we might ask. Given that 4x cubed y plus 3xy squared equals 2 plus 5y cubed, find dy dx at 1, 1. And we think, and someone made a guess. What was your guess? 3 is a great guess. So, all right, so that's the ideas for today. We will pick up again next time where we build off of this. Have a great day.